We are from Group 2 from Section 9. We'll be presenting about the case study project for Mission 4, SEEU 3533. So, without further ado, let's go. First one, what is amplitude modulation? So, amplitude modulation, or AM, is a technique used in electronic communication, most commonly for transmitting information via a radio carrier wave. In AM, the amplitude or strength of the carrier wave is varied in proportion to the information being sent, such as an audio signal, while the frequency and phase of the carrier remain constant. So these are some types or some variants of AM signals. So the first one is a double sideband full carrier, the SBFC, which have two sideband and a carrier. So the second one is double sideband suppressed carrier, the SBSC, which removes the carrier. So the third one is the single sideband SSB, so one sideband and a carrier. So the next one is single sideband suppressed carrier, SSBSC, so it only have one sideband. So the last one is the vestigial sideband, VSB, which have two, DSB and also SSB. So now we will present about the double sideband full carrier. So it contains two sidebands, the upper sideband USB and the lower sidebands, the LSB, and it have the carrier. So both sidebands are symmetrical, carrying the same information. The carrier is transmitted along with the sidebands, consuming additional power. So what are the disadvantages is that it is inefficient in terms of power and bandwidth usage. So it is commonly used in AM radio broadcasting. So you can see at the image is that, so when VM, the modulating signal, pass through to an AM modulator and also multiply with a carrier signal, and then thus the product is the VAM, the SBSC, the modulated signal. Now let's move on to the SBSC, double sideband suppressed carrier. So the carrier is removed, leaving only the two sidebands USB and LSB. So more power efficient compared to the SBFC, as the carrier is not transmitted. It requires a more complex receiver for the modulation since the carrier is absent. So it is used in some analog communication system where efficiency is critical. So you can see that the SBSC almost similar but have no carrier. So next one is the SSBSC. So it only have one sideband, USB or LSB is transmitted and the carrier is suppressed. It maximizes power efficiency and minimizes bandwidth usage. It requires highly accurate carrier synchronization at the receiver for the modulation. It is commonly used in high frequency communication such as military and marine audio. So as the name implies, single sideband, so only one sideband is used, whether it is USB or LSB. So the last but not least is the vestigial sideband, VSB. So it is a compromise between DSB and SSB, the dual sideband, also single sideband. It retains one full sideband and a portion of the other. Allows for simpler transmitter and receiver designs compared to SSB. It is used where bandwidth conservation is important but complete sideband elimination isn't feasible. Example, video signals. So it is widely used in television broadcasting, example NTSC and PAL system. So you can see the image of the vestigial sideband. So the modulating signal will go to the product modulator and carrier oscillator will multiply, and then it will pass through a sideband filter to get the VSB signal. That's all. Next is the demodulation. So what is demodulation? So demodulation is the process of extracting the original information signal, such as audio, video or data, from a modulated carrier wave. It is the reverse operation of modulation used at the receiver end in a communication system to recover the transmitted message. So as you can see the image, so this is the demodulation process. So how does demodulation actually works? It is because of an envelope detector. So an envelope detector is a simple circuit used to demodulate amplitude modulated signals AM by extracting the envelope, the varying amplitude of the modulated carrier wave. It is made of simple components like capacitor, resistor and diode. So this is what will happen. So when RC value is optimum, so as the name implies optimum, it have the minimal distortion value. So the second one, when RC value is too small, which is fast response, when it have a fast response, it is very sensitive to noise. The second one is RC is too large, so slow response. So when slow response, it cannot keep updated, so it will have a bigger distortion. Let us proceed with the next subtopic, which is the angle modulation. What is an angle modulation? So angle modulation is a way of sending information by changing the angle, either the phase or frequency of a carrier wave. Unlike amplitude modulation AM, which changes the wave strength amplitude, angle modulation focuses on how the wave phase or frequency shift. This makes angle modulation better at handling noise and interference, ensuring clearer signals. So there are two types of angle modulation: frequency modulation and also phase modulation. Only two, just remember. So what is frequency modulation? Frequency modulation, or FM, is a type of angle modulation in which the frequency of a carrier wave is varied in proportion to the instantaneous amplitude of the modulating signal. The amplitude of the carrier wave remains constant while the frequency changes convey the information. So you can see the equation. So these are the key components of frequency modulation: carrier wave, modulating signal and frequency deviation. Next is the phase modulation. Phase modulation, or PM, is a type of angle modulation where the phase of a carrier wave is varied in proportion to the instantaneous amplitude of the modulating signal. The amplitude and frequency of the carrier remain constant, while the phase carries the information. So that's the general equation. So these are the key components of phase modulation: carrier wave, modulating signal. There are no standard deviation for frequency. These are the relationship between FM and PM. So PM modulators can generate FM signals and FM modulators can produce PM signals, showing their close connection. Demodulation recovers the original information of the signal. So for PM demodulation, pass through a differentiator, then use a PM demodulator. You can see at the image down below. So for PM demodulation, pass through an integrator, then use an FM demodulator. So FM and PM are closely related, making it easy to understand one through the other. This is a quick comparison of PM and FM. So for features, variation of basis, FM frequency changes with signal, and phase modulation, phase changes with signal. So the noise immunity, frequency modulation has better noise immunity than phase modulation. So for implementation, so FM is common in analog communication, while phase is preferred in digital communication. So how about bandwidth usage? So FM is typically high, while PM can be managed more efficiently. So that's all. Thank you.
Hi everyone, today I will represent to you about 3 techniques in digital modulation.
Ask, amplitude shift keying. The carrier signal's amplitude changes to represent binary data. A high amplitude represents binary 1, and a low or 0 amplitude represents binary 0. Known for its simplicity and cost-effectiveness, ASC is widely used in optical fiber communication and infrared remote controls. However, it is sensitive to noise, making it less robust compared to other modulation techniques. FSK, frequency shift keying. The frequency of the carrier signal varies to represent binary data. A higher frequency represents binary 1, while a lower frequency represents binary 0. FSK is more robust against noise than amplitude shift keying, ASC, making it suitable for applications like radio communication. PSK, phase shift keying. The phase of the carrier signal is varied to represent binary data. Binary 1 is typically represented by a phase of 0 degrees, while binary 0 is represented by 180 degrees. PSK is highly robust against noise and interference. It is widely used in modern communication systems.
Did you all know what is multi-level shift keying? Here are the explanation about it. Quadrature phase shift keying, QPSK, is a digital modulation technique where two bits of data are represented by one symbol, enabling efficient data transmission. It uses 4 distinct phase angles to encode data, corresponding to the bit combination. That's all for radio digital modulation. Thank you for watching.
Latest innovations in modulation techniques. First is software-defined radio and cognitive radio. Second is hybrid digital analog broadcasting, HD radio. Third is digital modulation for 5G and IoT.
Next we will move to addressing common misunderstandings that appear in this chapter. Common misconceptions about radio modulation include health concerns, legal fairness, and cultural resistance. Scientific evidence from organizations like WHO confirms that RF emissions from regulated systems are safe, while policymakers can address spectrum allocation biases by reserving portions for smaller broadcasters. To ease the transition to digital systems and address cultural resistance, dual modulation schemes and affordable equipment can ensure inclusivity and accessibility for all. Lastly, these are the references, and that's all from our group. Thank you for watching our video.